We're on to number 11. The study compared the mean heights of fraternal twins where one is a boy and one a girl. The mean height of the female twins in their 20s is about 64.3 inches, standard deviation about 3.9 inches, females. The mean height of male of the twins, 69.9, and standard deviation 3.1. And the correlation between men and women in the male and female twins, about 0.75. So as pairs, twins, one's a boy, one's a girl, the correlation between their heights is 0.75. Suppose we'd like to predict the male twin height from the height of his twin sister. So that makes the male height y and the female height x in our regression line. Okay, and then it says, find the equation of the regression line. We're going to use these formulas here. We don't have the raw data, all we have is summary statistics. So with that, here's the regression equation, y equals a plus bx. The slope is b, the intercept is a. B is computed by correlation, standard deviation of y over standard deviation of x. We'll do that in a minute. And a is y bar minus bx bar. So we've got everything we need. We've got r, the means, the standard deviations. We're able to compute the regression equation. Here's the formula for b. R was 0.75. Y was males, the ones we're trying to predict. X is the ones we're using as predictors. So 3.1 over 3.9 times 0.75, it comes out to be 0.6. And then we put that b here. So y bar is 69.9 and x bar is 64.3. And here's b was 0.6 to get 31.32. And finally we get the equation of the regression line, 31.32 plus 0.6x. We did it. Make an accurate sketch. Well, we're going to sketch the line by taking some x and y values that we might expect to see in heights of adults. I went 50 to 80 inches, pretty well encompasses most values you might see in both sides. Here's women and men. And then on the graph I'm going to plot some points, so I'm going to put x equal to 50 and x equal to 80 into the equation. So there it is there, 50 in the equation, I get 61.32 out, and 80 into the equation, I get 79.32 back. And I plot those points. So 50, 61.32, and 80, 79.32. That's an accurate sketch. Predict the height of the brother from a sister who is 68. Here's 68 as an input. Put that in the equation and get 72.12. That's the prediction. Plot the prediction on your graph. I didn't do it. 68 and 72. Okay. Do you expect this prediction to be accurate? Well, I look at r squared. If r squared is not close to 100%, then the further away from 100, the less linear the pattern is, so the more scattered it is. So an r squared of 0.56 corresponds to a pattern that's pretty scattered out. It's a football of values. It's not just a line of values, so we don't expect that prediction. On average, it's accurate, but it doesn't predict an individual value very well because r squared is only 0.56. Rachel is 65 inches tall. Here she is. Predict the height of her brother Tom. Predicted value is 70.32. If Tom's actual height was 70 inches, find the residual. The residual is observed minus predicted. The observed height was 70, the predicted value was 70.32, so I get minus 0.32 as the residual. Cool. Here is a problem involving random sampling of 5 people. 18.2% have education beyond a bachelor's degree. If we sample n equal to 5 individuals, find the probability at least one is educated beyond the bachelor's. So if we set x equal to the number educated in 5 beyond bachelor's, then the probability x is bigger than or equal to 1 is because x has to be 0, 1, 2, 3, whatever. The only thing left is 0. So we could easily compute that by, that's probably x, that x is greater than 1 is 1 minus the probability x equal to 0. This is a binomial probability, so you could compute all 4 possible values of x can be 1, 2, 3, 4, 5 for x bigger than or equal to 1. Or we go to 1 minus the chance x is 0, so only remaining value. To know the probability x equal to 0, that means none of them have education beyond a bachelor's degree. The chance a single person doesn't have that education is 0.818, 1 minus 0.182. So 81.8% of the population aren't educated beyond a bachelor's degree. So the chance that all 5 of them don't have education beyond a bachelor's degree is 0.818 times 0.818 times 0.818, so 0.818 to the 5th power. That's all of them not beyond a bachelor's degree. So the 1 minus the chance they're all not beyond is the chance at least one is beyond, and that's 0.634. So 818 to the 5th power, my calculator's here, just to check that, double check that. 0.818 to the 5th power is 3662. One minus 0.366 is 0.634. Correct. Okay. And then we're on to number 15. I skipped over 14 because it takes too much space. We're using the random number table with line 130 to pick a random sample of size 8 from a list of 900 individuals. So the 900 tells us we're going to use 3 at a time because we're going to be numbering our individual 001 up to 900. Uses 3 digits. So we're looking for 3-digit numbers between 1 and 900. And so we'll go into the random number table and mark it off in 3-digit blocks. And since I don't know how many I'm going to have to use, I'll just take two lines to begin with. I couldn't fit it all here in one place, but here they are in 3-digit blocks. 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, leaving 1 at the end, unused. And in case we use those all up, I went to the next line and did the same thing. I didn't try to carry this forward, because ordinarily I'll just take and just draw a line in the table straight through a bunch of values. So I don't have to worry about keeping track of exactly where I am. We're always in the same place row after row. And here they are broken into 3-digit blocks. Okay, and we need just 8. So a lot of them will be between 1 and 900. So let's just start marking them off. 690, 516, 481, 7. These are all good. 1, 2, 3, 4, 5, 6, 7, 8. There they are. So you just go to the list of individuals you have, and you pull up 690, number 516, 481, 787, 174, 095, 178, 453, and you've got 8 randomly selected using line 130 in the tables. Alright, let's just take a look and recap for a second. So we found a regression equation using summary statistics. We used the multiplication property for independent events in random sampling because the individual samples chosen are independent of each other. And so we could find the chance that x is 0 and x is the number in a sample of size 5. Each one of them has to not meet the criteria. The chance that an individual doesn't is 0.818. All 5 together would be 0.818 to the 5th. And what we're looking for is the complement of that event. So 1 minus that probability is the probability of everything else, which is what we were looking for, and that's how we did it. Over here in 15, we took line 130, we marked it off in blocks of size 3, because we were sampling from 900 individuals. We actually did both lines just in case we needed them, but turned out we didn't. Because of the 900 being such a nice number, we didn't even get to the end of the first row in the table that we were using, and that's the end of that. So we're making some progress. We're done about 15 problems. I think I might have skipped one, I'm not sure, and we'll move on in a minute.